section 6.1, radians and the unit circle. So the goal is to, by the end of the class, to be re-familiarized with the unit circle, to practice it a little bit in pairs. I'm going to pair you up and practice it. And then do a little bit of homework on it. So, a little bit of information about an angle. We have what's called the terminal side of your angle. So if you draw an arrow over to the terminal side, sounds so final. The terminal side is the final position after a rotation about the vertex. And notice we're going in counterclockwise direction there, up from the initial side, which is the positive x-axis. So the terminal side, and then we have the initial side, the starting position of a ray. Remember, a ray is starts with a point and then has a directed arrow going in the direction that you want it to go. So there's from geometry, we have a line with arrows on each end. A ray has an arrow on one end, which shows the direction it's going, and then we have a segment that has dots on each end. And the ray that you constructed yesterday on the Smarty Radians worksheet just kept on going through all the circles. That was because all three of those circles, those concentric circles, look like a target. Circles are all similar. And so if it takes about 6.28 radians to go around the small circle, it's going to take about 6.28 radians to go around the middle one and the large one, because it's all based on the relative size of the radius of that circle. Standard position is an angle's initial side is on the positive x-axis. So right here is the positive x-axis. And then the angle comes up from there in a counterclockwise direction. So you can take angles that may be anywhere, located anywhere along the unit circle, and then transform them in such a way, rotate them in such a way that they land so that the initial side is on the positive x-axis, and then you can measure the degree measure of the angle or radian measure of the angle. Coterminal angles are angles that overlap with different rotations, plus or minus 360 degrees. So that would mean that they have the same terminal side. You could go around maybe 360 degrees, you land at the same spot again, another 360, and at the same spot. So, based on our activity from yesterday here, Smarty activity, maybe not. Smarty activity. Do you remember the definition for a radian? What is a radian? What is a radian? Yeah, it's the radius. It's the distance of the radius along the curve of the circle, right? So, also, in terms of degree measure, this goes back to geometry. The degree measure of the arc length, which is what you were talking about, is equivalent to the degree measure of the central angle, measured from the center of the circle. So same thing with radians. The radian measure, which is a length of how many radii, if we go one radii, it's just one radius length along the arc, corresponds to sweeping through a certain arc length. So that's what this is saying. A radian is an angle. Okay, a radian is an angle. It also measures arc length. But an angle whose terminal side sweeps an arc of length r. So when you measured the radius r to be 3 Smarties, then you put those 3 Smarties along the arc, that was 1 radian. Okay. The reason we use the ruler to connect from the center of the circle to the end of the Smarty arc was to show that corresponds to an angle as well. So radian is an angle whose terminal side sweeps an arc length of r, the radius of the circle. The unit circle just has a special r. It's centered at the origin with a radius r equal to 1. And so we're going to focus on the unit circle. And either I'm going to give you an input of radians, and you'll give me the ratio, the sine, cosine, or tangent ratio, or vice versa. I'll give you the sine, cosine, or tangent ratio, and you'll tell me the angle measurement. That's where we're headed with this. So you may have done this last year, converting from radians to degrees, degrees to radians, going back and forth. Those of you who are in physics, you're probably using degrees in physics. In math, you use radians. It's helpful to be able to go back and forth. When I introduce you to the special angles in radians on the unit circle, we'll look at it in terms of degrees and radians. It's good to be able to see both of them. Be able to, when you see 5 or 6, immediately know that's 30 degrees without even doing that conversion here. But if you want to convert something that's not a special, from an angle from a special right triangle, you remember how to do this? We like pi, at least when it's in terms of pi, so if the radian measure is in terms of pi, I'd like pi to cancel out. And so, do you remember the conversion factor? Conversion factor for this? It's either pi over 180 or 180 over pi, going one way or the other. So if I want pi to cancel out here, this is how I remember it. If I want pi to cancel out here, it's in radians, pi. Then it's 180 over pi. Now, radians don't always have to be in terms of pi, so that could mess you up. But it's 180 over pi when you want to convert from radians to degrees. So you might need to make a note of that. And so I think that's the first section of the homework. You're going to try one of these towards the end of the period. So negative pi over 10 times 180 over pi, then you got to cancel, simplify it. I'll let you do that. So why don't you cancel and simplify that and tell me what you get. Okay, so negative 18 degrees here. Pi's cancel out of negative 18 degrees. What does B simplify to? 72 degrees. And then C, 84 degrees, okay. So yeah, I just do some cross-canceling and cancel the pi's here. 15 goes into 180, it goes once into 18 with 30 left over. 7 times 12 is 84, so I would cancel first, multiply straight across. All right, converting from degrees to radians, we're going to do the reciprocal of that, so pi over 180. Pi over 180 and pi over 180. And so why don't you go ahead and simplify that and tell me what you get right here. All right, what do you got for the first one here? In radians. 5 pi over 12. Okay. And the next one is negative 11 pi over 12. Good. And then this one. What is it? 20 pi over 9, yep. There it is in radians. So converting, going one direction and the other. So there's a section in the homework on this, a section on this. A few problems of each. Number 3. It says state radian between 0 and 2 pi that's coterminal. Coterminal means it has the same terminal side. It just shares the same terminal side. I think it's helpful to draw a picture on these. If you want to, you can do the arithmetic. You're either adding 2 pi's, multiples of 2 pi. It can be 2 pi, 4 pi, 6 pi, whatever it takes to land yourself back around in a positive value that's between 0 and 2 pi. Okay, so it's like you just keep adding 2 pi's to it until you get there, or subtracting 2 pi's from it until you get there, one or the other. Okay. I like to just draw a picture rather than adding 2 pi's or subtracting 2 pi's. So let's draw a picture of this. Negative pi over 3 would be approximately down here because it sweeps through a negative here. And so if I wanted to get a radian between 0 and 2 pi that's coterminal, I'm going to have to go around 360 degrees or 2 pi radians. And so that's what my picture looks like. I'm adding 2 pi, which is the same as adding, if I multiply top and bottom by 3, it's 6 pi over 3. Getting a common denominator, so I end up with 5 pi over 3. Once you're a little more familiar with the unit circle and those special right angles, something like negative pi over 3, you will see that as 5 pi over 3, just I think immediately, just based on position where it's located. 5 pi over 3 is around in this fourth quadrant. If I add another pi over 3, I land back at 2 pi, or back at the positive x-axis. So add 6 pi over 3 to it. So you're going to be adding or subtracting factors of 2 pi. That's it. So 19 pi over 4. Let me draw a picture of that. I think it's helpful before I draw a picture, though, if you think of this as a mixed number. 4 goes into 19 4 times with 3 left over, so it's the same as 4 and 3 pi over 4. So what happens here is each time I go, each 2 pi, I'm back where I started, so I could go around 2 pi. And I go around another 2 pi. And then I go around about right here. So when I write that as a mixed number, I don't think I even need to take off 2 pi's. I could just lop off the whole number part of it, right? The 4 and 3/4 pi. So take off the 4, and what are you left with? 3/4 pi, right? So 19 pi over 4, which is equal to 4 and 3 pi over 4, is the same as just 3 pi over 4. If you'd like to, you could take off a couple of 2 pi's from this and keep doing that until you get to 3 pi over 4. If you write it as a mixed number, I think it's pretty easy to see. All right, negative 15.2. Where is that going to be located? Well, now let's think in terms of something that's not in terms of pi. Yesterday we learned that all the way around the circle once was about 6.28. That's what 2 pi is, right? 6.28 radians. So what's happening here is I have a 6.28, another 6.28, and a little bit left over. You see that? If I go around, let's draw a picture here. So there's a 6.28. And if I go around again, I'm going in the negative direction just because it's a negative number. There's another 6.28. And then I go a little bit more. Now the little bit more, I'm not sure that I have to kind of think about that a little bit. So what I'm going to do to this is add, basically, a 2 pi plus a 2 pi, or a 6.28 plus a 6.28 if you want. Now I'm still going to be negative here. 6.28 plus 6.28 is 12.56. So I still have a little less than negative 3 left to go. Do you remember halfway around the circle how many radians that was? Isn't it? It's 6.28 all the way around. So halfway around, yeah, be a little over 3, 3.14 is top. So 6.28 and 6.28 is about 12.56. 15.2 and 12.56 have a difference of around 3. It's a little less than 3. I'm going to land somewhere over here, just on my. So here it is. So it's kind of like this first one. I'm going to have to add 2 pi how many times to get a positive version of this? I'm still negative 2 point something over here. So I'm going to have to add another 2 pi to it. If you want, you can just keep adding 2 pi's to your negative number until you get your first positive number between 0 and 2 pi. Does that make sense? Just keep adding 2 pi's. No? You just keep adding 2 pi's to it. I have this negative number because you want a number between 0 and 2 pi. What is 2 pi equal to? Here's what I'm asking for. Give me a number between 0 and 2 pi. Well, okay, that's no problem with the one. Are you okay with these ones with pi's in it? Not really? Okay. So this is the same as 0 between. So here's what I'm looking for. I just keep adding 6.28 or 2 pi to it until I have a number that's lands between them. It's already in radian form.
Or like 30 times divided by 1.
Okay, we're not trying to convert it over though. We could, you convert, but that's, you should be able to just take it in radian form and just keep adding 2 pi's rather than change it to degrees and keep adding 360s. You're kind of doing the same thing. Yeah. So you're just adding or subtracting 2 pi's to it until you land with a number between these two. Okay. So if I add 2 pi plus 2 pi plus 2 pi or 6 pi, what is 6 pi equal to approximately as a decimal? 19 point something or 18 point something or anything. Okay, go ahead and let's figure what this equals here. Just do negative 15.2 plus 6 plus 6 pi for me. What do you get? 3 point what? 3.65. Okay. That's it. Just keep adding or subtracting 2 pi's appropriately until you land with a number in between one of these two. I think that's helpful to know. Move this over. That's all you're doing. So even if you don't want it, like you don't like the picture thing and trying to figure out how many times you're going around, just keep adding 2 pi or 6.28 until you land between 0 and 2 pi or 0 and 6.28. And if it's positive, just keep subtracting them until you land between those two. You might want to check it first. If it's positive, check. Am I already between 0 and 6.28 or between 0 and 2 pi? If not, I need to subtract multiples of 2 pi. So there's another section that will ask you to do that in here. It's one of these. All right, special right triangles. 30, 60, 90. It's something in geometry. Boy, we have a tough time with the bulk of students. This isn't you guys. You guys probably took the time to memorize it, but a lot of students just don't want to memorize this, but we use it all the time in trigonometry. So it's like now's the time. If you didn't get that last year in advanced algebra 2, you really need to know this. You'll use it often in calculus. It will just pop up at any time during the entire year, or for that matter, the entire sequence of calculus courses. It's just something you have to know really well, like your multiplication tables going into algebra 1. It's that important. So being able to know these special right triangles and being able to use the unit circle, well, it just will show up often. So, got a little wrap here, maybe to help you. So you ready? Yeah. I'm not going to wrap it for you, but here it is. For the 3060, here goes. 3060. Keep it on the down low. Use root 3. Use 2 times. So 3060. Keep it on the down low. Use root 3. Use 2 times. So here's how it goes. If I give you, you can. So that's the end of my wrapping career. Well, I'm going to do one more here. But 30 degrees corresponds to the shortest side. The use 2 times means 2 times the shortest side, and use root 3 means shortest side times root 3. It's all based on that shortest side. So 30 degrees. The side opposite the 30-degree angle is x. That's what that's saying. So the 3060, the 3060 is the one that has the root 3 in it, and also has the double, the shortest side. So do you remember this ratio? If I give you the shortest side, if I say the shortest side is 5, hypotenuse is 10, the side opposite 60 is 5 root 3. 45 goes like this, 4, 5, 4, 5. The answer is about to arrive. Use root 2. Legs are same. 4, 5, 4, 5. The answer is about to arrive. Use root 2. Legs are same. So what we mean by that is legs are the same. How do I know what the legs are? They look the same. That's true. That is how you know. And they're opposite the 45-degree angle, so you know they have to be the same. That's a geometric property. It says if you have, two 45-degree angles here, then the sides opposite the 45-degree angles have to be equivalent. This is an isosceles right triangle. And we say use root 2 means take x and multiply it by root 2. Now, I'd like to, well, we could probably do this. Let's go ahead and think about our special right triangles. We're kind of going to muddle through this part, and then I'm going to give you the unit circle. It's on the back of that sheet. There's a unit circle. And we'll go through and label all the special angles in both degrees and radians. And we will also add to that the coordinates that correspond to the special right triangles there. Now, you probably talked about this last year. Cosine corresponds to the x-coordinate. Remember that? The cosine is like the x-coordinate, and sine is the y-coordinate. Okay. Remember that? So x is cosine, y is sine. So if you can kind of, in your mind, picture the unit circle, picture the radian measures at each ray of the unit circle, and then have a coordinate to go with each one, an x and a y, then you know your cosine of and your sine of every angle. So if you and really all you need to know is that first quadrant, because then it just repeats and has different signs as you go around. I'll show you what I mean by that. We'll work through that. I think you've probably already done this before, but it's good with you. So the first time, though, we're going to just kind of muddle through this here. Sine of 0, and you could have your calculator out if you need to. We're going to think in terms of radians here, but sine of 0, which is equivalent to sine of 2 pi, would be, of course, equal to 0. So sine of 0, you can check it on your calculator, but sine of 0 is 0. If you'll recall, sine, we might want to write these down. I think we probably should. Sine of an angle theta is equal to opposite, remember SOHCAHTOA, over hypotenuse. Cosine of an angle theta is equal to adjacent over hypotenuse. And tangent of an angle theta is equal to opposite over adjacent. Opposite over adjacent. So sine of 0 is 0. That just means the opposite is 0 and the hypotenuse is 1, some number 1. In the unit circle it's 1. So when I draw my unit circle, let me just draw a unit circle for you. Just in case you're wondering, here's my unit circle. So when we're talking about sine of 0, it's right here, and this is the hypotenuse right here. So sine of 0 is 0. Now with the 30-degree one, now we're using this special right triangle, the 30, 60, 90 special right triangle. If I were to draw it on my little circle, and what a lot of my students do, even in the calculus, is they're drawing that picture every time they do one of these. They're drawing a picture oftentimes until they're just really familiar with it. But my 30-degree angle would be down low here. And if I draw in my right triangle, this is 1 right here, because the radius is always 1. It's on the circle. You with me? The radius is 1, so there's the 2x part. Meaning the opposite side is what? 0.5, that's right, or 1/2. Your calculator would kick out 0.5, but this is 1/2. And this right here would then be 1/2 times root 3, which we write as root 3 over 2. You with me? But that's how we figure out the coordinates here. It's like we take the 30, 60, 90 triangle, we place one of the vertices on the origin. The hypotenuse of that 30, 60 right triangle is the radius of the circle. Here's the short side, and here's the longer side. So this is 1/2 and root 3 over 2. So as a matter of fact, the coordinate here would be root 3 over 2, comma 1/2. No, root 3 over 2 first, and then comma 1/2. Because I'm root 3 over 2. What's the length of the x coordinate here? Root 3 over 2, and what's the length? 1/2. Now, what switches when you go to the other, the 60, 30, 90, if you will? Okay, if I switch to that triangle, the radius is still 1, but now what happens to these two coordinates? They switch, and that's the key. The 45, 45, 90 is easy. But if you can get the 30, 60, 90, understand that relationship. See, now, my coordinate up here, I'll do it in blue here. We'll overlap in blue. This is kind of an exaggerated 60 degrees to keep it away from the 30. But my coordinate switched to, now I'm only 1/2 over and root 3 over 2 up. And so the 60-degree angle is farther up and not as far out. When it's farther up, it gets the bigger coordinate. Root 3 over 2 is bigger than 1/2. Think about it. Square root of 1 would be 1. Square root of 3, you would agree, is bigger than square root of 1. So root 3 over 2 is the bigger or longer piece. So, man, if you can remember this red and this blue, you've got the whole thing, really. I mean, that's the key to it. is not mixing those up, and then you're there. So sine of theta, remember what I said, cosine is the x-coordinate, sine is the y-coordinate, or you can use the 30-60 right triangle, but sine of 30 degrees is going to be, by definition, the opposite, okay, you with me? Opposite, which is 1/2 over the hypotenuse, which is conveniently 1. So opposite over hypotenuse will give me 1/2. So we'll fill out this table. I don't expect you to, I think it's probably more helpful to work with a circle on the back side. But here's the table. So what did we say sine of 60 degrees was? It's root 3 over 2, because with the 60 degree, this blue triangle, the opposite is root 3 over 2, and the hypotenuse is still 1. So that one's root 3 over 2. And we're going to see some, I have it color-coded, there are some patterns here. If you have a highlighter or colored pencils, you could demonstrate some of the patterns. They're helpful. And then at the 90 degree, so sine of 0 degrees is 0, sine of 90 degrees, or pi over 2, is 1. Okay, because it's straight up here. And then sine of 45 degrees is going to be root 2 over 2. That's because with the 45, see, if this is equal to 1, okay, let's do a little algebra. I'll do it over here on the board. If x root 2 has to equal a radius of 1, what is x equal? Well, 1 over root 2, right? Just doing the algebra, dividing by root 2 here. Well, we don't write it like that because that's not simplified radical form. So what we do is we multiply by root 2 over root 2. Already learned all this back in algebra and geometry. So this is root 2 over 2. So that's where we get that ratio for sine of 45 degrees. Now, you know, cosine of 45 degrees is going to be the same thing. That's convenient. Tangent is going to be a ratio of these two. Remember, tangent is defined to be sine over cosine as well as opposite over adjacent. So if I have sine over cosine, I have it in order here. It's this over that. This over that is going to be that, yeah, 1. So root 2 over 2 over root 2 over 2 is 1. So if you can memorize that cosine is the x-coordinate, sine is the y-coordinate, then you can combine those together using the reciprocal properties of the other 4. Tangent, secant, cosecant, cotangent. Okay, if you know those definitions, the 6 trigonometric definitions of the ratios, the sides of the right triangles, and you know your cosine and sine, have these memorized, then you can figure out any of them. All right, so cosine of theta, so watch this. Look for the... So cosine of theta is 1 because I'm 1 over and 0 up. Cosine of 90 is 0, so you can see these flip-flop here. And then look what else flip-flops here. Cosine of 30 is root 3 over 2, whereas cosine of 60 is 1/2. And then when it comes to figuring out tangent, you just do sine over cosine. So 0 over 1 is 0, as opposed to 1 over 0 is undefined, right? So take this over this. Now, what about here? 1/2 over root 3 over 2. Let's do the arithmetic over here. So 1/2 divided by root 3 over 2 is the same as taking the bottom and multiplying it by the reciprocal. So 1/2 times 2 over root 3 gives me 1 over root 3. And 1 over root 3 is not in simplified radical form, so I'm going to multiply by root 3 over root 3, which is root 3 over 3. Okay, so this one is root 3 over 3. And then this one is conveniently the 2's cancel, leaving just root 3. Yeah. So there's the table. You can see all kinds of patterns in the table. That's one way to go about memorizing your sine and cosine of the special angles. Notice it's only the first quadrant. The only thing that changes as you go around is the negatives and positives. Okay. Any questions on that? Probably today as you go through and do this practice in pairs, you'll have the side. You'll probably actually have the other side out. Circle on the other side. And when I give a calculus review, like in the calculus textbooks, usually they'll have that unit circle that we're going to create today with all the angles and radians and coordinates on it. It's typically all they have. And we know what to do from there. We know cosine is the x, the first coordinate, sine is the second. We can go from there. All right. So here it is. I just want to talk a little bit about it, and then don't just start copying. Let's just talk just about the first quadrant, and then you can go ahead and copy it. Hopefully you can read this. You're like, what? Let me make it bigger. Oh, there, that's a little bigger. Can you see that? Okay, so this is 0 degrees. Equivalently, it's 360 degrees. 0 didn't show up there, but 0, 360. It's also 2 pi. So there it is. As I move up here, 30 degrees corresponds to pi over 6. If you were to do the conversion, multiplying by pi over 180, you get pi over 6, or vice versa. So pi over 6, pi over 4 is the 45, pi over 3 is the 60, pi over 2 is the 90. And then as you go around, the thirds are always high on the circle or low on the circle. So here's 2 pi over 3 is this high ray. 4 pi over 3 is this low ray farther away from the x-axis. 5 pi over 3. You'll hear me talking about either high or low on the circle as a way to think about is it root 3 over 2 or 1/2. If it's high or low on the circle, it corresponds to root 3 over 2 because that's the bigger of the two numbers between 1/2 and root 3 over 2. So why don't you fill that out here? I'll pause this for a moment. Okay, so right here we have 1, 0, and then as we go around, because we're farther out than we are up, it's root 3 over 2, 1/2. The 45, 45, right, just has two legs that are the same, both root 2 over 2, root 2 over 2. And then when we're higher up at this pi over 3 angle, it's 1/2, comma, root 3 over 2. And then 0 over 1 when we're straight up. So, yeah, we're just going to see repeats of these as you go around. Over here, we're farther up than we are out, so the x-coordinate's going to be the smaller of the two in absolute value. So it's going to be negative 1/2, comma, positive root 3 over 2. This one's going to be negative root 2 over 2, comma, root 2 over 2. This one's going to be negative root 3 over 2, comma, 1/2. And then here's negative 1, comma, 0. And then down here, I'm farther out than I am down, so the bigger in absolute value of the two, the root 3 over 2 is going to come first. So negative root 3 over 2, comma, negative 1/2. And then we have negative root 2 over 2, negative root 2 over 2. And then here is negative root 3 over 2, comma, other way around, negative 1/2. Let me fix this. It's kind of hard to write that way. So it's negative 1/2, comma, negative root 3 over 2. And then here is 0, comma, negative 1. And then here we're not as far out. It's positive 1/2. Farther down, negative root 3 over 2. And then here is root 2 over 2, negative root 2 over 2. And here we have root 3 over 2, comma, negative 1/2. And so those coordinates give you, I might want to write a note of this. These coordinates give you cosine theta, comma, sine theta, all the way around. And if you know cosine and sine, you can find any of the other four trigonometric expressions, find the values of them at those angles.